I think a key to really enjoy and appreciate biochemistry is to think like a molecule. But what does that mean and how can you do it? Well, it starts with having a really good understanding of what atoms and molecules are, as well as what like bonds are and what attractions are, and really how at the core of all of this is this idea of opposite charges attracting and like charges repelling, and the fact that molecules are made up of atoms that are made up of parts of little charged things, so they have positively charged things and negatively charged things, and those positively charged things have to stay put, the protons, but the electrons can move around, and so you often see them like just demonstrated as these like in these shells, and so that's helpful for a lot of things as I'll get into. But really the whole the fundamental like aha thing for me to try to like get into a biochemistry mindset is really thinking in terms of like electron clouds. So like where you can predict like where these electrons are most likely to be in like orbitals and stuff. But actually these electrons are moving around, and based on where they are in relation to like the number of protons and all of that stuff, you can get these charged regions, and then going back to that opposite charge attract, boom, you've got an attraction. And so really thinking about this cloud thing can really like shift your perspective and really just like help you understand what's happening, as well as just trying to figure out which regions of a molecule will be more reactive, which will be less reactive, when will you get an actual bond formation. So all of these different things, if you try to conceptualize more in these various ways that at least have been helpful for me. And so I just wanted to go over some of that, as well as really what is an atom. I just speed off a bunch of like jargon, like atom, molecule, electron, proton. Don't worry, I'm going to get into all of this. And I just wanted to give like kind of an intro in a way that is kind of how I approach biochemistry and how I think about molecules, and hopefully it'll help someone else get a deeper appreciation and help them kind of have us get an intuition for talking and thinking like a biochemist. Starting back from the beginning, so like what is an atom? So an atom is basically like the unit, like a piece of a certain element. So with elements, we're talking about like carbons, hydrogen, oxygen, nitrogen, all of these different things that you'll find on a periodic table. And the atom is like, if you were to buy like a piece, I mean, not like a chunk of gold, but like the smallest like thing that if you make it any smaller, it's no longer that thing. So you can't, if you take a carbon atom, you can't split it up any further and still have carbon. What defines an element is the number of protons. So there are three main subatomic particles: protons, neutrons, and electrons. So protons and neutrons, they hang out in this central part called the nucleus. And the protons are positively charged and the neutrons are neutral. So the neutrons don't have a charge, but they do have an important role because they kind of help glue the protons together. So an important concept that we'll be talking about over and over is that like charges repel and opposite charges attract. And so we have a bunch of like charges. We have all these positively charged things right here. And so they're going to be repelling each other, but the these neutrons, they kind of just like glue it all together and really form this strong, dense central core. So you see it's like this little dot, and this isn't even to scale, but this electron cloud around it is huge, and this is where the electrons hang out. And so the electrons are really, really teeny tiny, and they're negatively charged. So the actual mass is actually coming almost entirely from the protons and neutrons, and we don't really even like consider the masses of the electrons because they're so teeny tiny, but they're super important because they're what's actually going to interact to like form bonds and that sort of thing. So the number of protons defines the element. So that means, so like and the number of protons is like this number above the symbol in the periodic table. So this like atomic number. And so a carbon is always going to have six protons. Nitrogen, 7 protons. Oxygen, 8 protons. Hydrogen, 1 proton. If they have a different number than that, they're a different element, period. But the number of electrons and the number of neutrons can vary. So the neutrons, those are neutral. So if you change the number of neutrons, you don't change the charge of the atom. But you can change like the stability of the nucleus. So sometimes if you have like too many neutrons or that sort of thing, the nucleus can get unstable. And so then it can actually like undergo radioactive decay. And so the nucleus kind of like rearranges and like can shoot out like particles and stuff. And so some nuclear isotopes are unstable and they're radioactive, but not all of them are. So an example would be deuterium, which is a heavier isotope of hydrogen that is not radioactive, whereas tritium, which is another hydrogen nuclear isotope, is radioactive. But anyway, so neutrons can vary, but you're not changing the charge or anything, and we don't really think about these like nuclear isotopes that much in biochemistry, except when we're like making use of them in the lab, because we can use radioactive isotopes. So like labeled, if you use one of the like heavy, so we refer to heavy or hot as like or I guess we refer to them as hot if they're radioactive. They can be heavy but not radioactive, but we can use that to those versions of it to label and like track molecules. And the reason we can do that is because you can change the number of neutrons without really changing the properties of the molecules, so they'll still like act just like the normal version of the atoms. But if you change the number of electrons, you do change the properties, because you're actually introducing like a difference in charge. So the overall charge of an atom, so in the neutral form, the number of electrons is equal to the number of protons, because they have equal and opposite charges. So if you have equal numbers, then you don't have a charge. But if you have an imbalance, so if you have an unequal number of electrons and protons, then you get a charged molecule, and we call a charged molecule an ion. So ions are like have a full charge difference. So they either have more, if they're positive, we call them a cation, and they have a fully positive charge because they're like missing an electron. So basically they've like donated to something or something. And then if you have an extra electron, then it's an anion. And as we'll see, when these stick together, we call them ionic bonds. But you can also have partially charged regions of different molecules. And so now we need to talk a little bit. Now we're moving away from atoms and into molecules. So molecules is basically when you have like atoms joined together through covalent bonds. And so now we get back to our dog walking analogy. Okay, so bear with me. So with the electrons are really in this big cloud. And you can kind of, it's easy to, for a number of reasons, it's easy to conceptualize the electrons as hanging out in these sort of like shells or orbitals. And so these in this like shell notation or whatever, like, so the first shell has can hold 2, and then this one holds 8. And this helps with various things, because like the outermost electrons are what we call valence electrons, and they're the most highly energetic. They're the farthest from the pole of the protons. So remember, the protons are positively charged and these electrons are negatively charged. So the protons are kind of tasked with helping rein in those electrons. But the electrons that are really far out, they're going to be freer. They have more energy. They're not like resisting the pole so much because it's like farther away. So they don't have to be as, it's easier for them to roam. And so these valence electrons are the ones that are actually the most reactive. And so when we do the shell model, we can see which ones are like the valence electrons. And so this makes it really helpful, especially because for various reasons, atoms like to have a full like a full outer shell, which is often an octet for the ones that we're talking about here. And if we look at our periodic table, we can actually, like, the ones go, if you look down a column, they'll have the same number of valence electrons. And so they'll also have similar properties because they'll want to get to that same, they'll need the same number of electrons to gain or lose in order to get to that ideal number, that full outer shell. So there are reasons why it makes sense, and it's helpful to think about things in this shell model, but things are really more complicated, and these electrons are actually like moving around. So this is, don't worry about the bonding part of it yet, but these electrons, instead of actually being in like shells, they're more like they're in these various orbitals. So they're different shape orbitals and that sort of thing. And then when they bind, they join together, then they form like shared orbitals. But the whole point I want you to get is that these electrons, it really is like when we show them as like even being in one of these like orbitals, that's like a probability distribution. So these electrons are flowing all the way around. They're like, and they're super, super tiny. And so if you were to kind of like track them, so if you were to put like a GPS or something on this electron, you'd see it like moving all around. But where it's the most, where you're most likely to find it is in like one of those orbital spaces. And so that's why it's helpful to do things like that. But these electrons are moving all around, and that has important consequences because they're not like stable around one spot. You can get shifts in the electron density that, so the electrons are hanging out more with one region of a molecule than another, and that'll give you charge and differences in like polarity and stuff. And the way that they can get to that full shell is like through covalent bonding, where they can actually share pairs of electrons and actually like merge their electron clouds. So it helps me to think about this sometimes in terms of dog walkers. So your atom, your like the nucleus, so where the protons and neutrons are, that's like your dog walker, and it's holding all the leashes. So it has this positive charge that's pulling in all of your dogs, which are the electrons, and they're negatively charged, and they want to be free. Especially those valence electrons that are super far out and they can't hear the nucleus calling out its love as much. But some atoms, for various reasons, like shielding and number of protons and all of this stuff, have a tighter pull over their electrons. So they have like tighter leashes. They're holding on tighter. We call these electronegative. So these are like your electron hogs. Other and common examples are like oxygen and nitrogen. Other atoms don't have as tight a pull. So like a hydrogen, its dog is kind of less loyal. And so if it hears that call of the oxygen, oh, I love you dogs, then it's going to come on over and it can actually join up. And so you can get the atoms to kind of form up in bonds. And so then you have them all joined together. And so that's just one way that you can think about this. But an important thing is that the oxygen, when you have an interaction like this, the oxygen's love is so strong that it's going to like influence those electrons from the hydrogen as well. So when they join together, they're like merging their like electron clouds, and they're still going to hang out more with the oxygen, even though that electron was like originally from that hydrogen. Its loyalty isn't that strong. Like it's going to hang out more around the oxygen. So if you were to look at the electron cloud, it would that electron would be found more commonly towards the oxygen. And this has an important consequence called, this consequence is can manifest as polarity. So basically a polar molecule has a separation of charges, and this is because like the electrons are hanging out in one area more than another. I'm sorry, I'm trying to find the slide that where's my polarity slide? I don't know where my polarity slide is, but this one will work. So you have this like separation of charges. So because the oxygen is electronegative, it's going to be pulling more on those electrons. The electrons are going to spend more time near the oxygens than they are near the hydrogens. So this is going to make the hydrogens partly positive and the oxygens partly negative. And this sets you up for having partial charge interactions that are really important because basically all interactions are based at least on temporary charges, as we'll see in a minute. So it's the whole concept, going back to opposites attract, is really at the heart of all of biochemistry. Even molecules you wouldn't think that are actually charged, as we'll see in a minute. Ionic bonding, which is really more like a strong attraction. So with that, you actually have, so like you can gain, one gains electrons, one loses electrons. So you have these like fully and partly charged things, but then they just kind of hang out together because of their difference in charges. And so it's really just a strong attraction, and they're not actually like merging their clouds. It's not like an actual bond. And then you can have weaker versions of this. So somewhere in between this covalent bonding and this ionic bonding. So not as strong as this because you don't have actual full charges, but you have partial charges. And there are a bunch of different ways that you can do this. And you just have to have like a partial charge, so like a separation of charge. So ions have a full charge because they have a difference in protons and electrons. Then you have permanently polar molecules like water, which have permanent dipoles. So they have a permanently positive part and a permanently negative part. So their electrons are unevenly spread out, and then they can get attracted to ions or other molecules with a permanent dipole or even a temporary dipole. So even non-polar molecules can be made temporarily polar if they come close to like an ion, because their electron clouds can then shift. Or another permanent, they can also be induced by like a permanent dipole or even a temporary dipole. So there are these things called London forces or dispersion forces, where it's basically you just have like an instantaneously dipole induced dipole. And so basically the electrons, because the electrons are like moving all over the place, if they just like happen to all hang out in one side of a molecule, now you have polarity, you have this like charge region. And then if they're next to something else, then all these electrons in one area, and then another molecule comes in, and they're gonna like all those electrons are going to like run away. They're gonna get repelled from that area, and then the thing that they're next to, and they're next to, and so you get this like chain reaction of this forces. However, it's only as strong as its weakest link, and so if you disrupt just one, the whole chain can depolarize. And so these sort of like London forces or dispersion forces, if you have a lot of molecules, they can be really strong. Like this is how the gecko can like keep its feet on the wall and on the ceiling. But the gecko can also move its foot, right? Because it would be bad if it was stuck there permanently. So these type of charges can be really strong if you have a lot of molecules, but they can also be disrupted and reformed. There's a special type of non-covalent bond or like attraction. I don't like the word bond for things that aren't actually like covalent bonds because I think it gets confusing, but that's actually the term that we use. So it's like, but you can think of these really as just attractions that are somewhere in strength between like those normal like non-covalent interactions, so like those London forces and that sort of thing. But so they're stronger than those, but they're not as strong as the ionic bonds or the ionic attractions, because those are where you have those full charges. With a hydrogen bond, what you have is you have like a donor and an acceptor. And the donor is going to be a hydrogen that's bound to something electronegative. So the electronegative thing is going to pull the electron density away from the hydrogen. And this is going to make the hydrogen partly positive. So usually this donor is like a hydrogen attached to an oxygen or a nitrogen. So often in an alcohol, so an OH or an amine. And so you'll commonly see these in like the backbone of a protein side chain or in the bases of nucleic acids, as we'll see. Or in a common example, water. So these hydrogens are have this partial positive charge because they're getting their electron density pulled away from them by this oxygen. So, and then on the other side, you need the acceptor. And so that's going to be something that's electronegative and it has a lone pair of electrons. So it needs that lone pair because that's actually what's going to like be able to form this interaction. And so it's hogging electrons, so it's partially negative. And so this is often an N, or this should be an O. So it's often an N or an O. And this allows you to have these acceptor-donor interactions, and that you can form these networks. And so water forms these really strong hydrogen bonding networks. And so actually a lot of the, like some of the drive for reactions to occur is actually like entropy driven. So entropy is the like tendency towards like disorder. And so if you like take molecules that are tightly held and then you make them freer, so you set them free, then that's like energetically favorable. And so sometimes actually when you have a binding interaction, a main like driving force is actually that you're disrupting that water and freeing all those water molecules. So that was just an interesting thing that I learned kind of later on in my education, but I thought it was really interesting. But anyway, so yeah, so such hydrogen bonds are really important for helping hold together like chains of DNA, as well as the protein backbone. But so basically atoms can share pairs of molecules to form these to form covalent bonds. They can also sometimes when they share, so they share like a single pair to form a single bond. A double bond can be shared they're showing 4 electrons. And then electrons can also exist as unbonded lone pairs. Sometimes when you actually have electrons shared between more than 2 atoms, we call this electron delocalization or resonance. And it's kind of like a communal sharing. So basically it has like this it makes the bond like extra strong. And so you see this a lot in like ring structures like benzene, as well as carboxyl anions and amide bonds. So the like peptide bonds, the bonds in proteins, making it the protein backbone. And they're really strong, but they have to be like in a plane. And this restricts the motion of the peptide. So this is an important source of strength for the peptide backbone, but it has various consequences on the structure and how things can move. But yeah, so this is called resonance stabilization. And it when it happens in a ring, we call it aromaticity. And so you can actually see like, so the sigma bonds, so the s orbitals, that's where like the normal like single bonds form, and then you have these p orbitals, and they're joining side to side, and then they can be delocalized in these pi bonds, which look kind of like these donut-y things, but they're like above and below the plane. But the whole point, like I don't want to go into like all this orbital theory and stuff, which I'm not an expert in at all. But the point is that they're really like these clouds and that the electrons are moving around, and that's what I really want you to see from that. So how do molecules actually form these covalent bonds? There are different ways. So going back to the idea of like an electronegative atom. So that's one that really likes, that like really tightly pulls on its electrons. When we're talking about like a We can also talk about nucleophilicity. So a nucleophile is something that really wants it really wants positive charge. It has like more electrons than it can comfortably handle. So it wants some help. So going back to our dog walker analogy, it's like a dog walker that's kind of overwhelmed with dogs. So it likes having dogs, but it wants a little help. And so nucleophiles often have a lone pair of electrons, which is I was taught you can think of it as kind of like a happy face. So you have this lone pair over you. So you see nucleophiles are commonly like atoms with lone pairs. So these are usually on an oxygen or nitrogen. Also like double and triple bonds, so like the pi bonds can form as nucleophiles. So they like having that extra electron, especially if it's like filling their octet or their whatever their outer shell is. So they want to share it. And then they have to find something that wants electrons. And so something that wants electrons is an electrophile. So we call these nucleophiles, I don't remember if I said this a second ago, because the protons are in the nucleus. So they're seeking another nucleus, another dog walker to help them out, basically. With an electrophile, they want more dogs. So they want more electrons. So these are things that with like too few electrons or electron density. So sometimes they are positively charged, but not always. And sometimes the nucleophiles are negatively charged, but not always. And sometimes you'll find them they'll be like atoms that are attached to electronegative things. So for example, a lot of these interactions that we'll see, a lot of the like common electrophile in biochemistry is actually the phosphorus in phosphate groups, because the oxygens are really electronegative, so they're pulling away the electron density from that phosphorus. So if you were to go and you take a picture of where the electrons were, they would be hanging out. They'd be hanging out with the oxygens more than the phosphorus, and this leaves the phosphorus partly negative and subject to attack. So you can get things like substitution, where you have a nucleophile attacking. You can have elimination. So basically, there's just these various mechanisms where you can have nucleophiles and electrophiles interact, and that's a common way in which bonds can form in molecules. And so those are all those like strong covalent bonds. And then remember that the non-covalent bonds, so everything from your full-on ion charge, ionic bonding, to the weakest, like the London forces and the hydrogen bonding that are somewhere in the middle, all of those are just, they're just like attractions based on charges that are either permanent. So they're either full permanent charges in the case of the ionic, and sometimes we call ionic bonds salt bridges when they happen like in proteins. They can be partial, they can be based on like permanent dipoles, so neutral molecules overall, but they have a charge separation. They can even be based on just like temporary induced dipoles, or in just like instantaneously, like randomly, these electrons are over here, and now the ones next to it are going to shift over. And so it's a lot easier to think about all of this when you're really thinking about things as being more like a cloud than like a shell. So if you think about the cloud and the electrons moving around in the cloud, I think that I find it a lot easier to think about things in that way. So you have the shifting cloud, and you're thinking really more about electron density, as opposed to like a shell model where you're trying to actually like where exactly is that electron like on a ring, because it's not really on a ring like that. And so those rings are really helpful when you're trying to figure out like which molecules will interact to form like a covalent bond. But when you're thinking more about the whole concept of where in a molecule is going to be partially charged or negatively charged, which molecules will form these like interactions, these attractions, as opposed to the actual covalent bond forming, then it's really, really helpful to think about things in this cloud way. And so, yeah, so I hope that helped.